So in Chapter 6, we're going to be looking at solutions. Solutions are homogeneous mixtures of two or more substances. So when I use the word homogeneous, I'm talking about a uniform mixture. Everything is dissolved, it is consistent throughout. So solutions consist of two parts. So they're made up of a solvent and a solute. So definitions of solvent and solute. A solvent is the component that's present in greater amount. Okay, so this is usually oftentimes water. So when you are making a solution, say salt water or sugar water, you are dissolving the sugar in the water or dissolving the salt in the water. So the medium in which the solid is being dissolved is called the solvent, and it's usually in greater amount. The solute is the component, therefore, in lesser amount. So in the example of sugar water, the sugar would be the solute because you have less sugar than you do the water that you're dissolving it in. Salt water, same thing. Now there can be more than one solute. So for instance, I could take water and I could dissolve some sugar in there, but I could also dissolve some salt in there. So in that case, sugar's the solute, but so is the salt. And the solvent then is just the water, what I dissolved it in. So a lot of the aqueous solutions that we've been talking about in labs, the solvent is the water. So when I say aqueous solutions, remember I mean those solutions with that little AQ by it when we're writing out those chemical reactions. So when we took copper sulfate, for instance, in one of the labs we did, you might have watched the video where Dr. Rennie was weighing out the solid blue copper sulfate, and then he added that solid blue copper sulfate into water, dissolving it in the water, making an aqueous solution. Usually when we think of solutions, we think of liquids. And most of the time solutions are liquids, but they're not always. So a solution can be a gas. It can also be a metal. So an example of a solution that's a gas would just be the air that we're breathing. Because the air that we're breathing right now is made up of several different components. We have oxygen, we have nitrogen, carbon dioxide, among other things. So it is a mixture, a uniform, homogeneous mixture of two or more substances. An example of a solid that is a solution would be an alloy. So brass, for instance. Brass is an alloy and it's made up of copper, and it's also made up of zinc. Okay, so the reason that it's still classified as a solution is because it's a homogeneous mixture. The copper and the zinc are present in the same amounts throughout. They are mixed uniformly. We actually did the calculation in one of our past labs, getting 67% of one of the metals and 33% of the other. So it's always in that same ratio of copper to zinc. Liquid solutions is what we're going to focus on, however, in this chapter. So we talked about electrolytes briefly in a past chapter when we were talking about ionic compounds. So ionic compounds, when they dissolve in water or to make a solution, since they have those ions present, those positive and negative charges, they can conduct electricity. They're called electrolytes. So in the example below, we have a solid, that's what the S is for, sodium chloride, and we are dissolving it in water. Okay, so this is forming a solution. We have the sodium chloride as the solute, the thing that's being dissolved, the thing in lesser amount. We have the water, the H2O, as the solvent, greater amount, the medium in which the solute is being dissolved. When this happens, when we dissolve sodium chloride in water, since it's an ionic compound, it separates into its sodium cation and its chlorine anion. So it's charged components. Notice there's an AQ written after each of these ions. That's because they are now an aqueous solution. They have been dissolved in water. Non-electrolytes, on the other hand, do not conduct electricity. So when we talked about covalent compounds, we said that they can also dissolve in water, but they do not dissociate, which means since they're not ionic, since they're not made up of charged components, since they're sharing their electrons, they don't break apart. Okay, so we have a similar situation here. We have solid sugar, that's what this chemical formula is. We are dissolving it in water, and it does dissolve, as we can see on the reaction or the product side of the equation, because it has an AQ by it. That AQ is saying it has dissolved in the water. It is now a solution, it's homogeneous, dissolved. Okay, so it still dissolves, but it doesn't break apart because it's a covalent compound, all nonmetals, and they are sharing their electrons. So when we talk about solutions, we often talk about solubility. Okay, so in order for something to dissolve, it needs to be soluble. And we looked at this in Vesper theory when we talked about the molecular structures of things. So how much solute will dissolve in a given solvent is the definition of solubility. So how much sugar can I get to dissolve in that amount of water? Okay, and in order to even figure out if it can dissolve, we can apply that like dissolves like rule. Okay, so in order for two substances to make an aqueous solution, in order for one to dissolve in another or be soluble in each other, they need to have those similar polarities. So when we looked at it back in chapter 4, we had, if you had a polar substance and another polar substance, then yes, they would be soluble in one another, which means they would dissolve in one another. They would be uniform throughout, they would make a solution. Okay, but if you had a polar and a non-polar, so they're not similar polarities, they're different polarities, then they would not be soluble in one another. Okay, now oftentimes with solubility, especially when we're looking at solids and liquids, if we increase the temperature, we can increase the solubility. Okay, and this mainly applies to solids and liquids. However, with gases, increasing the temperature does not help. Okay, what helps gases is increasing the pressure, for instance, or lowering the temperature. So a good example of this is soda. So you have a soda pop in your refrigerator. Okay, why is it in your refrigerator other than the fact that it's nice to have a cold beverage if it's on a hot day? Well, putting the soda, a carbonated beverage of any sort, in the fridge actually helps the gas, so the carbonation, the CO2 molecules, stay soluble. It helps them dissolve in the liquid. Okay, because carbon dioxide, and that's the bubbles, that's the gas present in carbonated beverages, it is a non-polar compound. And water, which is the base for most sodas and other carbonated beverages, is a polar compound. So they have different polarities. So they're not soluble on their own. So in order to help make those CO2 molecules soluble, we lower the temp by refrigerating carbonated beverages, and we increase the pressure by having those cans pressurized. When you crack a soda can, you can hear the pressure release. You can hear those CO2 molecules come out. So since we're talking about solubility, we just talked about some ways to increase solubility, whether we were increasing the solubility of a solid or a gas. So when you increase that solubility, so you can have a saturated solution. So what saturated solution means is the maximum amount of solute is dissolved in that solution. Okay, so if you think of making Kool-Aid, when you used to have to make Kool-Aid, it was actually a packet of flavoring, and you added that packet to the water, but then you also had to add sugar to the water. Okay, so if you're adding sugar to the Kool-Aid and you're stirring it and you're stirring it, If you put too much sugar in, what would happen is it would stop dissolving and you would have solid sugar at the bottom of the Kool-Aid. Okay, so that's when the solution, you knew the solution was saturated. No more sugar could dissolve, the sugar being the solute. No more sugar could dissolve. That's the maximum amount of sugar that could dissolve in that water. Now, by altering the conditions, you can actually create a super saturated solution. So what that means is, if I took that Kool-Aid, okay, and we said increasing temperature can increase solubility. So if I took that Kool-Aid and heated it up, what I could do is make that solid sugar that was present at the bottom dissolve, because I would be increasing the solubility of that solute by increasing the temperature. Another good example of this is making hummingbird food. So I make hummingbird food often, and how I do it is I heat up the water and then I add the sugar when the water is already hot. So the water being my solvent, the sugar being my solute. So by heating up the water first, what I'm doing is I'm making that sugar more soluble. I'm creating a supersaturated solution. The problem with supersaturated solutions is that eventually that solute, that sugar, is going to come out. So dynamic equilibrium, we're going to bring this up again in the next chapter. We're actually going to talk about this term quite a bit, so it's important to know this term. But I want to bring it up here in this example because it applies to saturated solutions. What dynamic equilibrium is when you have a saturated solution with extra solute, some's going to dissolve and some will precipitate out, and it's going to happen at the same rate. So the key with dynamic equilibrium is that this dissolving and precipitation rate is the same. So let's go back to the Kool-Aid example. So say I added too much sugar to my Kool-Aid, and I have some solid sugar particles at the bottom. I have a saturated solution with solid at the bottom that can't dissolve because the maximum amount of sugar has already been dissolved. Okay, so dynamic equilibrium, what it's saying is the sugar that's dissolved is precipitating out, which means it's going from being dissolved to forming a solid sugar at the bottom. And the sugar that is currently at the bottom is dissolving at the same rate. So the amount of sugar at the bottom of the Kool-Aid is the same the entire time. Okay? However, those sugar molecules that are at the bottom are not the same molecules because some of those molecules are dissolving at the same rate that new molecules are precipitating out. They're basically replacing that solid with ones that were previously dissolved. We'll look at more examples of this to try to solidify that concept of dynamic equilibrium. Henry's law. So what Henry's law is going to refer to is gas solubility. Okay, so we've been looking a lot at liquid solubility, so let's talk about gas solubility. And what Henry's law states that the number of moles of a gas dissolved in a liquid is proportional to the partial pressure of the gas. Basically, you increase the pressure and you can increase the solubility. Also notice that gases are most soluble at low temperatures, so it's different than solids, right? When we're talking about sugar, a solid, we wanted higher temperatures for it to dissolve, for solubility to occur. But with gases, you don't. You want low temperatures. Okay. Also, going back to the soda can, right? It's under pressure, and we put it in the fridge at low temperatures to increase the solubility of that CO2 gas. Applying it to some other real-life examples, it's the reason why we give O2 to raise the amount of oxygen in the bloodstream. So if someone's low on oxygen, you give them a stream of O2 to breathe in 100% oxygen from an oxygen tank. And what you're doing by allowing them to breathe in 100% oxygen is you're increasing the pressure of oxygen in their lungs, in their body. And that increased pressure is going to make oxygen more soluble in their bloodstream, increasing the oxygen in their blood. So another example, this is the reason for decompression sickness. So Henry's law does apply to decompression sickness. So when I talk about decompression sickness, what I'm talking about is nitrogen. So think of someone diving. So this often happens with diving. So a diver goes in the water, they go very deep in the water. When they go deep in the water, they have lots of pressure on them, right? Because all those layers of water are applying pressure to their body. And since they have more pressure on their body, they have nitrogen bubbles, or not nitrogen bubbles, sorry, nitrogen gas dissolving in their bloodstream, because increasing pressure increases solubility of the gas. So by having so much pressure on them, they have more soluble nitrogen molecules in their blood. And if they come up too fast, if they decrease that pressure too fast, what happens is when you decrease the pressure, you're decreasing the solubility of those nitrogen molecules. And if you decrease the solubility, you're going to get bubbles forming in your blood, and that can be very dangerous. So they often have compression tanks for divers when they come back up that try to simulate the pressure, trying to get those nitrogen bubbles back being soluble in the bloodstream so that they can't cause damage. So here's just a visual for you talking about the soda can. So in this visual, these are the CO2 molecules here, the black middle atom with the two red atoms on the sides. Notice CO2 molecules, and we've drawn this on several occasions actually. I think it was even a test question at one point. Carbon's in the middle with an oxygen on either side, and it is a linear molecule. That's why it's non-polar. Okay, so these are the little CO2 molecules. They're dissolved. The reason they're dissolved is because they're under pressure. As soon as you open that pop can, what happens is those CO2 molecules, you release the pressure so they're not as soluble anymore. So now they can escape. So here are some concentration equations that we're going to be using in this chapter. And concentration is basically a measurement of how much solute is dissolved in the solvent. So what percent, for instance, is solute? So looking at these, we have mass volume percent, and this is where we want grams of solute, so we need to know the definitions of solute and solvent to use these equations. So it's grams of solute divided by milliliters of solution. Now I want to point out the units first off. So when you're approaching these problems, and I do have a video where I'm working through and using these equations so you can see that, but I want to make sure that you're looking at the units, and that the units are, if they're not in the correct units, convert before you put them in the equation. So mass volume percent, you need the solute in grams and the solution in milliliters. So get it in the correct units and then plug it in. Notice since it's a percent, we are multiplying it by 100 because that's how we make it a percent. Going down to the next equation, we have mass percent. So very similar to mass volume. The numerator has grams of solute, just like mass volume percent did, but since it's mass percent, instead of milliliters of solution, we're going to have grams of solution. And since it's a percent, we are multiplying it by 100. The next set of equations are parts per thousand, parts per million, and parts per billion. So these equations are very similar to the mass percent. So if you look at the equations below, I have grams of solute in the numerator, just like I do for mass percent. I also have grams of solution in the denominator, just like mass percent. The only thing that's different is instead of multiplying by 100, for parts per thousand, I'm going to multiply by 1,000. That's what this 10 to the third is. It's the same as saying 1,000. For parts per million, same equation, but instead of multiplying by 100, I'm multiplying by 1,000,000. And that's what 10 to the 6th is. If you enter 10 to the 6th in your calculator, it'll add the zeros and show 1,000,000. And of course, last but not least, parts per billion then, instead of multiplying by 100 like we did in mass percent, we're multiplying by 1,000,000,000, or 10 to the 9th. Now here are even more concentration equations. So you're probably wondering why there are so many. often depends upon what you're measuring. So for instance, the first equation on this sheet is molarity, represented by a capital M. Molarity is what we most often use in chemistry. And the reason for this is because we use moles in chemistry. Notice the equation is moles of solute divided by liters of solution. Well, in chemistry, we use moles all the time. We're always converting from grams to moles or moles to grams. So this makes sense as a concentration calculation in the chemistry field. I also want to point out, notice I said liters of solution. Okay, so in the previous equations that we looked at, mass volume percent, the volume was measured in milliliters. So really be aware of your units when you're going through these word problems and convert accordingly. Molality sometimes is used in chemistry as well. Molarity is more often. I want to point out molarity with an R and a capital M only differs by one letter than molality. So you really have to be looking closely when you're doing these calculations. Also notice molarity with an R is represented by a capital M. Molality with an L is represented by a lowercase m. And you do calculate them differently. Even though the numerator in both cases is moles of solute, it's the denominator that's different. So we are dividing moles of solute when we calculate molality by kilograms, and notice it's just the solvent. So not the solution as a whole, but just the solvent portion. And remember, the solvent is the medium in which the solute is dissolved. The solvent is the one in greater amount. Most often in this course, the solvent will be water. Moving on to the dilution equations below. So I will work through a dilution example, and you do some dilution equations in the solutions lab, which I think is the last lab of the semester. So you will be using this equation in lab as well. But I want to point out how it looks very similar to some of those gas equations that we used in the last chapter. Because notice we have two molarities, it's a capital M, that's how I know it's a molarity. And we also have two volumes. So what's going to happen when you're doing a dilution calculation is you're going to be given 3 out of the 4 variables, and you're going to have to rearrange the equation to solve for the fourth. Now it does say that the volume needs to be in liters, and to be honest, it doesn't necessarily need to be in liters. It can be in milliliters. You just need to make sure that the volume is consistent on both sides of the equation. So what I mean by that is if you have milliliters as your V1, then your V2 also needs to be in milliliters. However, if your V1 is liters, then your V2 also needs to be liters. So just consistency is what's key here. So let's now look at some colligative properties. So colligative properties depend upon the concentration. So that's why we're bringing it up here on this concentration chapter when we're talking about solutions. So colligative properties depend only on the concentration of the solute particles, but not on the identity. So what I mean by that is, for instance, if I'm talking about a salt, say I'm talking about sodium chloride, and I'm seeing what the concentration of a sodium chloride solution is. Okay, then I'm looking at a solution of potassium iodide. It doesn't matter that one's sodium chloride and one is potassium iodide. So the identities themselves don't matter. What matters with colligative properties is the concentration. So sodium chloride, doesn't matter that it's sodium chloride. What matters is what is the concentration of that sodium chloride solution. So the 4 colligative properties that we're going to look at are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So we're going to talk about vapor pressure lowering and boiling point elevation. So these 2 colligative properties we're bringing together because they go hand in hand. So what vapor pressure is it results from the escape of solvent molecules from the liquid to the gas phase. So what that means is the vapor pressure affects how many molecules go from liquid to gas. So think of boiling water on the stove. Water is a liquid. When you boil it, some of those liquid water molecules go into gas water molecules, or water vapor, it's often called, right? So to decrease a vapor pressure of a liquid, what you can do is add a non-volatile solute. So going back to the example with boiling water on the stove, a lot of people add salt to their water when they're boiling it on the stove. Oftentimes, the reason for this is to flavor whatever you're cooking in that water. So when I think of boiling water on a stove, I'm probably going to put some sort of pasta in that water. So adding the salt adds flavor. Well, salt is a non-volatile solute. So by adding that salt, what you're actually doing is you're decreasing the vapor pressure of the liquid. And when you decrease the vapor pressure, you're decreasing the amount of molecules that go from a liquid to a gas. So what that means is you are increasing the boiling point of that liquid. So sometimes people add salt to water because they think it's going to help it boil faster. And it might help it boil faster because it's creating some nucleation sites for the water to boil around, but it is actually increasing the boiling point of the water. So the water needs to get hotter in order for it to boil. So freezing point depression is another colligative property, and this is where you lower the freezing point of a substance by addition of a solute. So in the previous slide, when we talked about boiling point elevation, what we were doing was adding a solute to increase the boiling point of a substance. Well, here we're going to be adding a solute to decrease the freezing point of a substance. So an example of this is adding salt on the roads to melt ice in the winter. Now, we don't do that often here because winters don't get that cold here, but oftentimes up north they do this to make the roads safer, to melt the ice. So how this works is you add salt to the ice on the roads. By adding this salt, this solute, you are decreasing the freezing point of water. So say water freezes at 32 degrees Fahrenheit. If I add a solute to it, a salt, what I'm doing is I'm decreasing that freezing point. So instead of water freezing at 32, it's now going to freeze at 25. And the reason this is a colligative property is because it's dependent only on the concentration. So the more salt I add, the higher I have the concentration, the better it's going to work, the more ice it's going to melt. Okay. Another example would be ethylene glycol, and that's antifreeze. We add this to car radiators in the winter to prevent the freezing of the coolant. So antifreeze is a solute. It is an additive that we add to lower the freezing point of coolant so that it doesn't freeze up our lines in our vehicle in the winter. The last colligative property we're going to talk about is osmosis. So you've probably heard of osmosis before, and what it is the diffusion of water through a semi-permeable membrane. So when I talk about diffusion, I mean it's a movement of either a solute or a solvent from an area of high concentration to an area of low concentration. So it's essentially trying to equal it out. So if I have on one side of my membrane high concentration, what happens is there's a slow spread of that solute through the membrane until the concentration equals out on both sides of that membrane. With osmosis, we can talk about osmotic pressure. And what that is, it's the pressure that's exerted to stop the flow of water or another solution across the membrane. So due to osmotic pressure, that's what allows the concentration to equilibrize, essentially. Now I do have an equation on this slide, and we're not going to use it to solve for anything. Okay, this is just trying to show the concept of osmosis. So we can actually use the ideal gas law, and in place of P we can put this pi symbol, and that pi symbol is representing the osmotic pressure instead of our classic pressure that we talked about in chapter 5. There's also another term called osmolarity, and this is the molarity of the particles present during osmosis. Okay. Osmosis is often used in kidney dialysis machines. They use this concept for kidney dialysis machines to try to take over the filtering function of the kidneys. So they have a membrane that solutions can pass through, and that membrane stops the particles, the ions that they don't want to carry through, while letting the ones that they do want to carry through. So let's go back to those electrolytes in solution. So when we talked about electrolytes at the beginning of the chapter, we were talking about ionic compounds, essentially, that dissociated in an aqueous solution and that had the potential to conduct electricity. Now, we can actually measure the concentration of electrolytes by using what we call equivalence. So I have a calculation down here showing exactly how we calculate what we call equivalence, and that is the concentration of ions or electrolytes in solution. So to calculate equivalence, we're going to take the charge on the ion. And when I say the charge, I mean the magnitude of the charge, not the actual charge. So for instance, sodium's a +1. Well, what I'm taking is the 1. I'm not taking the charge. So if I had a negative ion, for instance, I wouldn't bring the negative into the equation. I would just bring the number after the sign into the equation. So solving for equivalence, we take the charge per ion, the magnitude of the charge, and we multiply it by the molarity. So in these types of problems, you're going to be given the molarity of the ions, the concentration of the ions, but you're also going to be given what the ion itself is, and you need to take the charge into account when calculating equivalence. So the two examples I have below, we have a molarity of 3, and we're going to take that molarity and we're going to multiply it by the charge on the ion, and sodium's a +1, so it's just 1 times 3. This gives us an answer of 3 equivalents per liter. The next example, also the same concentration as with the sodium ion, but we also need to take into account the ion itself. And in this case, magnesium is a +2 ion. So we are taking the charge of 2, multiplying it by the concentration of 3, and we get 6 equivalents per liter. So why are ions important? Why do we want to calculate equivalence at all? Well, there are 2 important cations in bodily fluids, and I don't mean there are only 2. I am a chemistry teacher. I am not an A&P teacher. I do not know how many or what other ones are. These are 2 that I know of, and I just wanted to use them as examples. So sodium cation that we just looked at in the previous slide is an important ion in your blood. It's important for several reasons, some of which being if your concentration is too low, this can affect your urine output, it can cause dry mouth, it can cause possible fever, right? So if you are having these issues, you want more sodium in your diet. High concentrations can also be bad. So it's important to know what the concentration is in your blood. You can actually take a blood sample and test, figure out what the equivalents per liter are, and see if it fits in the appropriate range. If you have a high concentration, this could possibly mean that you have diabetes or other complications. Potassium, K+, is another ion that's important, intercellularly and in your blood. So if you can test for K+ ions in your blood, and if you had high levels, this could indicate that you have an injury. Because when you have an injury, it causes large numbers of potassium, K+, in your blood sample because cells have ruptured, releasing those ions. Okay, so this can help figure out internal injuries, for instance, that maybe you didn't know you had. Because if your levels are high, they try to look for the reason why. So the normal range for potassium in your blood you'll notice I have listed here. It's between 3.8 and 5. And notice the units. The units are MEQ/L. So what does MEQ mean? Well, it's an equivalent like we calculated on the previous slide, but it's milliequivalents. So think of your metric to metric scale. It's on the milli side. Okay, so if you can take a sample of your blood, test it for potassium ions, if it doesn't fall in this normal range of milliequivalents per liter, then it could possibly mean that you have other issues that need to be resolved within your body.